So the scenario here is we have this, this beam or lever or whatever you want to call it, resting on a fulcrum that's 2 meters from one end and 3 meters from the other end. And somebody's standing over here pushing down with a known angle, an angle of about 37 degrees. So what we want to do is we want to figure out all the forces and torques acting on this. We want to know, among other things, we want to know, for instance, how much force is this guy pushing with? Because that's currently unknown. What we can do, though, if we just draw a free body diagram for an object here, and what object do we really care about? What's the one object that has lots of forces on it that we want to figure out? If you could choose just one object to analyze here, what would it be?
The beam.
What's the one object that pretty much everything is acting on? Yeah, the beam itself. If we take a look at the beam is experiencing lots of forces. So what we're going to do is we're going to draw out a free body diagram for the beam itself. And usually for a free body diagram, we just treat the beam as just one single point. We can often treat an object as just one single point and look at all the forces acting on it. This would be called a free body diagram, or sometimes a force diagram. Versus if we care about the actual shape of the object and where the forces are located, this is usually called an extended free body diagram. That's free body. I mean, the body in this case is the plank itself, just the object. Free body in the sense that we're looking at this object in isolation. We're not looking at any of the other objects connected with it. So we're looking at only the forces acting on this object. And what forces would we want to include here? What are some forces acting on the beam?
The person pushing it.
Yeah, there's this person pushing on the beam. That's a force. So we'd have a force of the push. So in our free body diagram, we just draw that as an arrow in this direction extending outwards from that point. So we've got force of the push. And the force of the push is an unknown magnitude. We don't know how strong this force is, but it did at least tell us the direction. It told us that it's a direction of 36.87 degrees, presumably below horizontal. I'm just going to round that off to 37 for now. Although anytime a problem mentions the angle 36.87 degrees, that angle is usually chosen for a reason. This shows up all the time in math and physics problems. Because if you take the side lengths here, if you wanted to know what these side lengths are, how would you figure that out, assuming this is a right triangle? How would you figure out how these side lengths, let's say the opposite and adjacent sides, are related to each other?
Inverse tan.
Yeah, if you take the inverse tangent, try that out on a calculator. What is inverse tangent of 36.87 degrees?
It's 88.45.
As the inverse tangent? Are you in radian mode or degree mode? That seems pretty high.
I think I'm in degrees. Yeah, I'm in degrees.
Inverse tangent. Can you say that number again?
It's inverse tangent of 36.87, right?
Oh, I've got that mixed up. That should just be tangent because we know the angle. We know the angle. We're trying to find the side lengths, right? Tangent of an angle equals a ratio of side lengths. Inverse tangent takes a ratio of side lengths and gives you an angle. In this case, we have the angle, so we want to take the tangent of it to get the side length ratio. So sorry about that. What is the tangent of 36.87 degrees?
0.75.
0.75. That's almost exactly 0.75, so almost exactly 3/4. In other words, the ratio of this side to this side has to be the ratio of 3 to 4. One example would be side length 3 and side length 4. Or it could be any multiples of that, as long as it's proportional. You might have like 30 and 40, or 6 and 8, or 0.03 and 0.04. But as long as the ratio is 3 to 4, then that makes a 36.87 degree angle. And this is also a very convenient set of sides, because in that case, what would the hypotenuse be? Or how would we find that hypotenuse? If you know two of the sides are 3 and 4, what would that hypotenuse have to be?
5.
Yeah, 5. 3 squared plus 4 squared would be 25. Square root of that is 5. So anytime you see specifically an angle that's 36.87 degrees, that looks suspiciously precise. But anytime you see this angle, that's probably because somebody is deliberately trying to set up a 3, 4, 5 right triangle to make the side length, to make the numbers easier in the side lengths. So keep an eye out for that. Anytime you see this angle, that's probably because it's somebody deliberately setting up a 3, 4, 5 right triangle. And that's exactly what we're going to get here. The magnitude is going to form a nice 3, 4, 5 ratio with the x and y components. So we should expect whatever this push force is, we should expect the x component to be 4/5 of that, and the y component to be 3/5 of that. Of course, we're not really going to need that information until later. And in fact, we could do the whole thing with just sine and cosine of 36.87 degrees. But it's a good thing to watch for. Anytime you see this angle, that's going to lead to a 3, 4, 5 right triangle. Any questions on that so far? And what other forces do we know have to be acting on the beam? If the beam has a mass and it's near a planet, what other force would you expect to be acting on it? And we've got to have gravity, right? Gravity's going to be pulling in which direction? Gravity pulls straight down. So we're going to draw that as this downwards arrow from the object. And we can even figure out how strong that is. How do you usually calculate the magnitude of force of gravity?
mg.
Yeah, m times g. We know the mass here is 20 kilograms. And gravity, are we using 9.8 for gravity, or are we rounding it off to 10?
10.
So rounding off gravity to 10. mg is going to be 20 times 10, so that's 200 newtons approximately. So that would be the weight of the object. The mass is 20 kilograms. The weight is the force of gravity, so that's going to be the 200 newtons. So we've got a 200 Newton downwards force of gravity, an unknown diagonal force of the push. The thing is, those can't be the only forces though, because if the only forces were these, the object's going to be accelerating down and to the right. So what other force is going to be there to balance this out? What's preventing the beam from just falling?
The force of the triangle.
Yeah, the force of this fulcrum here that it's balanced on. And that's going to be, usually we'd expect a fulcrum force to be straight up. It can't just be straight up though, because it's got to also be preventing it from sliding sideways. So presumably the force of the fulcrum is going to be up and maybe to the left. And in a lot of cases, we wouldn't really even draw in an arrow yet for force of the fulcrum. We know there is a force of the fulcrum, but we don't really know for sure how strong it is or in which direction it is. So we would often just leave that blank. In this case, we have a pretty good idea which direction it's going to be in. We know it's got to be canceling out these forces together. So it's got to be opposite to sort of somewhere in between them. And probably pretty strong also, because it's got to balance out everything else. So something like this. We don't know exactly what yet though. And what do we know about all three of these forces? If this object is just staying still, What does that tell you about these three forces? Is this object accelerating?
No.
And if there's no acceleration, what does that tell you about the forces?
They're balanced.
They've got to be balanced. In other words, they all add up to
0.
0. And this is usually called Newton's first law. Newton's first law is the idea that no acceleration means no net force. And that's true in both directions. So this is a bidirectional if then. If the object is not translationally accelerating, then the total force is 0. And the other direction, if the total force is 0, then the object is not translationally accelerating. No acceleration and no net force are synonymous. So we know that at least that these forces add up to 0. The very fact that the object is not accelerating, even if it was moving, if it's not accelerating, if the velocity is not changing, then you know all these forces acting on the object have to add up to 0. So we can start with that. We can say that all these forces, the sum of the forces is 0. However, we're in a two-dimensional situation here. We've got forces in the x and y directions, including diagonals. So this idea that the forces add up to 0, this is really two equations because we can split these vectors into components. So instead of just saying the forces add up to 0, we can separately say the x components of the forces add up to 0 and the y components of the forces add up to 0. The sum of the forces in the x direction add up to 0, and the sum of the forces in the y direction add up to 0. So each one of these forces can be split into components, and then we can write out two equations. For example, x components. What forces have x components at all? Do any of these forces have x components? Yeah, Fg does not have an x component. It's purely in the y direction. So if we're looking at just x components, we could ignore the g, the force of gravity. We just got force from the fulcrum has an x component in the negative direction. Force of the push has an x component in the positive direction. So those two x components have to add up to 0. Let's say force of the fulcrum in the x direction plus force of the push in the x direction add up to 0. That's one equation. It's still got these two unknowns. We don't know the force of the fulcrum in the x direction, and we don't know the force of the push in the x direction. And then also in the y direction, looks like everything here has a y component, or at least could have a y component. We don't really know anything about the force of the fulcrum, but it at least could have a y component, so we should include that. So we've got this unknown force of the fulcrum in the y direction. We've got an unknown force of the push in the y direction. And we've got a force of gravity in the y direction. But for gravity, we do know the y component. What is the y component of the force of gravity?
0.
It's not going in the y direction at all?
Oh wait, just kidding. Isn't it just 10 times the mass?
Yeah, so that'll be 200 Newton. Well, 200 Newtons is the magnitude. But since it's going purely in the y direction, that also tells us the y component. In fact, Fg as xy components could be written as what, comma, what?
0, 200?
Yeah. Although it's pointing downwards, so we probably treat that as?
Negative?
Yeah. 0, negative 200 Newtons. So the magnitude of the force of gravity is 200 Newtons, but since that's straight down, the y component is negative 200 Newtons. So we could actually fill that in right now, negative 200 Newtons. And note that we are formally still adding the forces. We've got y component for the fulcrum plus y component for the push plus y component for gravity equals 0. It's just that the y component for gravity happens to be a negative number. At this point, we now have two equations, but how many unknowns do we have?
2.
2. And what are those two unknowns? What variables do we not know here?
Well, actually, is it 4?
Yeah, it looks like we've actually got 4. I mean, we only have 2 unknown vectors, the force of the fulcrum and the force of the push. But each one of those vectors has 2 unknown values, the x component and y component. So if you consider the components separately, we actually have 4 unknowns. The unknown x component of the fulcrum, unknown y component of the fulcrum, unknown x component of the push, and unknown y component of the push. So we're going to need more information here. We're going to need more equations. Ideally, if you have 4 unknowns, you need 4 equations in order to solve for the 4 unknowns. But there's some information we can get from just the geometry of the situation. Like for the push, we don't know how strong the push is, but we at least know the direction. So we can use some trigonometry. In fact, we can use the trigonometry we were just looking at earlier with that right triangle. Going back to this force of the push, let's say FP, we want to split that into an x component and a y component. FPX and FPY. And all we know is this angle is 36.87 degrees. So what does that tell us about FPX and FPY in relation to FP itself? For instance, if you wanted to figure out, like let's say we know FP, how would you find FPY?
You would do sine if you knew FP.
Yeah, you could say sine of this angle equals opposite over adjacent, so that's FPY over FP. And then we can multiply both sides by FP. And find that the y coordinate is just sine of this angle times FP. And what's sine of 36.87 degrees? What should we expect the ratios of these sides to be if the angle is specifically 36.87 degrees? This is specifically the angle of what type of right triangle? Yeah, 3, 4, 5. And of course, that doesn't mean that this side length is exactly 5 newtons and this is exactly 3 newtons and this is exactly 4 newtons, but it has to have those ratios. The ratio of FPY over FP has to be the same as the ratio of 3 to 5. In fact, this essentially just tells us what sine of 36.87 degrees is. Since the 3, 4, 5 triangle has a 36.87 degrees angle, that means any triangle with that any right triangle with that same angle has the same ratio. Sine of 36.87, opposite over hypotenuse, is 3 over 5. So we know this sine of the angle can be just written as 3 over 5. Likewise, cosine of 36.87 degrees should be what ratio? Yeah, it's going to be 4 over 5. Cosine of 36.87 degrees is 4 over 5 because that's adjacent over hypotenuse in the 3, 4, 5 right triangle. And any other triangle with those same angles, it might be a different size, but it will have the same ratio of side lengths. So we know that FPY is 3/5 of FP, and likewise FPX, that's just going to be cosine of this angle times FP, and cosine is 4 over 5. So we know FPX is exactly 4/5 of the force of the push. FPY is exactly 3/5 of the force of the push. Although which direction is it in the y component? If this is down and to the right, we should be treating the y component as, negative. So we're going to need to insert an extra negative here. So FPY is negative 3/5 of FP. But we can now make these substitutions. Everywhere we see FPX, we can replace it with 4/5 FP. Everywhere we see FPY, we can replace it with negative 3/5 FP. So let's fill that in. We know FPX is just 4/5 FP. And we know FPY is negative 3/5 FP. And the advantage of doing this, making these substitutions, is we now have, instead of two equations with 4 unknowns, we now have only 3 unknowns. We've got an unknown fulcrum X force, unknown fulcrum Y force, and we have an unknown push force, but we at least don't have to worry about the X and Y components. We've already figured out what the X and Y components are in terms of the push force. So we've reduced those 2 unknowns into just one unifying unknown. And so now there's only 3 unknowns instead of 4. If we can get one more piece of information, we'll have 3 equations, 3 unknowns, and that's something we can solve. Any other questions on those substitutions so far? And I'm going to make a note of those components off to the side in case we need them later. We know that FPX is 4/5 FP, and FPY is negative 3/5 FP, where FP is the actual magnitude. Often, formally we should probably be writing this in the double absolute value bars, but often we write magnitude of a vector as just that variable without the vector sign on top. That usually means magnitude of the vector. So to get one more equation, we've got all the information we can get out of just the forces. Forces adding up to 0 gives us these 2 equations. We're going to need one more piece of information. And what else can we do here? What else has to add up to 0 in this case? We know the forces add up to 0 because there's no translational acceleration. But what else is this object not doing? What other kind of acceleration is not happening? There's no translational acceleration, and also there's no...
Rotational?
Yeah, there's no rotational acceleration. This object has speed 0 and continues to have speed 0, so there's no translational acceleration. It's also not rotating and continuing to not rotate. It's not changing the fact that it's not rotating. There's no rotational acceleration. And so for this, we can use the rotational version of Newton's first law. Rotational Newton's first law, which is if there's no rotational acceleration, that means what sort of thing has to be happening to cause rotational acceleration? What's the rotational version of force?
Torque has to be applied.
Yeah. To cause a translational acceleration, you need to apply a non-zero force. To cause a rotational acceleration, you need to apply a non-zero torque. You've got to have some off-center push causing it to rotate, or causing it to change its rotation. It might already be rotating. The important thing is rotational change. So in order to have no rotational acceleration, you need to have no torque. The torque, or maybe there are torques, but the torques add up to 0. The sum of the torques has to be 0. So this is going to be our third equation. We get 2 equations from the fact that the forces add up to 0, 2 because we're in a 2-dimensional universe. Or at least the forces exist in a 2-dimensional universe in this context. But we can get a third equation from the fact that the torques also have to add up to 0. And this is really where the idea of the extended free body diagram comes in. The free body diagram is great for showing how much force there is and in which directions. But torque is not only about force, torque is also about where the force is. Stationary, yeah, equilibrium, formally equilibrium just means all the forces add up to 0 and all the torques add up to 0. But you can interpret that as if it's at rest, it's going to stay at rest forever. Or if it's in motion, it's going to continue that motion exactly the same forever. But for our purposes, equilibrium, in particular static equilibrium, means everything's staying still and not changing. It'll just continue staying still forever. So that's what we're dealing with here. This is a static equilibrium problem in the sense that this object, the beam, is not moving and not rotating. And most importantly, it's continuing to not move and continuing to not rotate. There's no rotational acceleration. There's no translational acceleration. So we can assume that the forces add up to 0 and the torques add up to 0. There's also the idea of a dynamic equilibrium problem. Dynamic equilibrium means that the object is moving, but it's not accelerating. So even though it's in motion, you can still assume that the forces add up to 0 because there's no translational acceleration, and the torques add up to 0 because there's no rotational acceleration. So it's the same basic idea. Even if the object is in motion but not accelerating, you'd still assume that forces and torques add up to 0 individually. But that dynamic equilibrium tends to be somewhat different to work out because there's different forces that could be acting on a moving object versus a stationary one. But it's still the same idea that the forces have to add up to 0 and separately the torques have to add up to 0. So let's try this extended free body diagram. Let's see if we can draw all the forces acting on it in terms of where they are. And the free body diagram without showing location can still be useful just for quickly listing out all the forces that could be acting on it, but then put those on your extended free body diagram so you can look into where they are as well. So we've got this beam. If we list out all these forces, including where they are, we know we've got the push at this far left side here. And we've got a fulcrum that was, I think the fulcrum was 2 meters into it. So 2 meters from one end, 3 meters from the other. And I'm going to leave this kind of incomplete because we don't know exactly how strong this is or even which direction it's in. And then also the force of gravity. And where should we expect the force of gravity to be located? Where would we actually draw that?
The middle of the beam.
Yeah. In the absence of any other information, if we're not given information about like how the mass is distributed, we should generally assume that the gravity is located in the exact center. Exceptions to that would include, like, let's say this object was made out of a non-uniform material. Maybe this is made out of some sort of wood where like one side of the wood is heavier and the other side of the wood is lighter. In that case, we would assume that the center of mass, the location where gravity is applied, is closer to the heavier side. I guess I should try that a little longer. But the idea is that gravity is influencing every single molecule in this entire beam. But we can treat it, instead of treating it as lots and lots of little tiny forces, we can treat it as just one big force located at an average position. And that average position is the center of mass or center of gravity. So we have all these forces now labeled on an extended free body diagram, showing the force's direction and location, where the force is. And now we can go back to the idea of torque. How do we usually calculate torque? How is torque defined in the first place? At least in terms of its magnitude.
Radius times force perpendicular.
Yeah. Or alternatively, you could write that as perpendicular radius times the entire force, or as radius times force times sine of the angle. But I think this is actually going to be the most useful one here because we are already splitting up these forces into components anyway. And those components, like the X components, are parallel to the moment arm, the lever itself. And the Y components are perpendicular to the lever itself. So these components are going to be useful, and we're already splitting it into these components, so we may as well make use of them. To calculate those torques, though, we've got the forces. We're going to need some radii, the actual distances, or moment arms. And that means we're going to need to measure from a pivot point. What location do you want to call the pivot point here? If this were rotating, what would you expect it to rotate around?
Would it be either the fulcrum or like where you press down?
Yeah, I would say probably the fulcrum. The force of the push, the thing is, if the push is too strong or too weak, it's going to make this rotate, but it's going to rotate around the fulcrum. The fulcrum is the pivot point here, or at least it's the hinge that everything's rotating around, the axis of rotation. So let's treat that as the pivot point. And by the way, if the object is not rotating, you could actually choose any location as the pivot point. If the object is rotating, then of course the point that it's rotating around, the axle, is the pivot point. If it's not rotating, you could choose any location as the pivot point. But choosing this location is going to be very useful mathematically here, because the force of the fulcrum then is at the pivot point. If a force is at the pivot point, how much torque does it produce?
0.
0. Because if it's at the pivot point, we've got 0 radius and therefore 0 torque, no matter how much force it is. The nice thing about this is that that means any force at the pivot point doesn't produce any torque. So if we choose the pivot point to be at a location with a force we don't know, then that's one less unknown. The force of the fulcrum is not going to influence our torque equation at all. So you can make the torque equation considerably simpler by choosing a pivot point at a location where there's a force you don't know and don't care about. So let's choose the location of the fulcrum as our pivot point, partly because it makes sense that that would be the point it would rotate around, but mathematically because this means that the fulcrum is an unknown we don't have to worry about. Our only torques are going to be from gravity, because that's some distance away from the pivot point. That's our R value here. And the force of the push, because that's also some distance R away from the pivot point. And what are those distances? How far is the push from the pivot point here? Based on that original diagram, how far was the pivot point from the end of the beam?
2 meters, I think.
Yeah, that was a 2 meter distance. And also, if we're assuming force of gravity is located in the exact center of the beam, how far is that from the fulcrum? What was the total length of the beam?
Right, in the whole thing?
Yeah, the whole thing was 5 meters. So the pivot point, or the center, would be how far from one end?
2.5 meters.
Right, 2.5 meters. If we've got 2 meters from the end to the pivot, how much further from the pivot to the center?
0.5.
Yeah, this is just half a meter. So we've got from the pivot to the force of the push is 2 meters, from the pivot to force of gravity is 0.5 meters. So we can now fill those in as torques. We can calculate the torque associated with each one. So using the R times F perpendicular, I think that's going to be most useful here. We can say torque from gravity, for instance, is 0.5 meters times 200 newtons. Because the radius is 0.5 meters, the perpendicular component would be the Y component, which is just 200 newtons here. So 1/2 times 200 would be 100 Newton meters. And then torque from the push, we can multiply the radius times the perpendicular component of the force. And of the components, which component is perpendicular to the radius here? If we've got a 2 meter distance, what would you say the perpendicular component is? Would that be the y component or the x component or something else entirely?
The y component.
Yeah, the y component, if we actually split up the push into x component and y component, the y component is perpendicular to the radius, whereas the x component is parallel to the radius. So the y component, or the perpendicular component, is just FPY. And we also know FPY happens to be negative 3/5 FP. We can ignore the negative for now because we're just looking at magnitude. But torque from the push is 2 meters times 3/5 FP. Or 2 times 3 would be 6/5 FP. And also meters. But we can probably ignore the units at this point. So we've got torque from gravity, torque from the push, and we know the fulcrum exerts no torque at all because it's at the pivot point. So we can just say these add up to 0 because we know the net torque is 0. One thing we've got to be careful with, though, is direction in terms of assigning positives and negatives. How do you decide the direction of a torque?
The right-hand rule?
Yeah, you can use a right-hand rule for this. And the right-hand rule I usually use for this, to figure out the direction of a torque. First of all, torque has to be in a direction along the axis. Like if this object is rotating, if this object were to rotate, it's going to be rotating around an axis in which direction? What would be the axis of rotation here? If it rotates like this or like this. Which direction, like if you were to build an axle, if you wanted to make this rotate like this, would you put the axle like this or like this or like this? Which direction would you orient the axle to allow this to rotate in this way?
Perpendicular.
You definitely want it perpendicular to the beam. But note that that could be in any of these directions. These all count as perpendicular to the beam. For instance, this axle would allow the beam to rotate this way, but that's not the direction we want. We want the beam to be able to rotate this way. So we want an axle that's pointing straight in and straight out of the board. So this axle allows the object to rotate in the direction we want. So the axis of rotation is straight in and straight out, which means the torque is going to be straight in or straight out. So that's what we're going to have to decide. We can choose the torque as either straight in or straight out. Another thing to keep in mind is that by definition, the torque vector is going to be perpendicular to the force that causes it. And also the torque vector is going to be perpendicular to the radius vector. This is just part of the definition of torque. So if you have, for instance, let's say we're talking about the force of the push. The radius is to the left. The push is down and to the right. So we've got our radius vector and our force vector. Those two vectors together form a plane. And the torque has to be perpendicular to that plane. So the radius vector, force vector form a plane. The torque vector has to be perpendicular to that plane, something like that. So we know that the torque here has to be pointing either straight out of the board or straight into the board, because that's the only way it can be perpendicular to both the force and the radius. So the only option left is it straight out or straight in? And note that we can do all that without even doing the right-hand rule. Before we even use the right-hand rule, these perpendicular properties narrow it down to, in this case, either straight out or straight in. The right-hand rule is just to determine which one of those it is. And one way to do the right-hand rule is to put your hand at the pivot point, stretch out your fingers straight along the radius, that is, fingers straight towards where the force is located, but then curl your fingers in the direction of the force. Because note that if all I'm doing is pointing my fingers straight along the radius, I can still tilt my hand around like this. I can still swivel like that. But I want to swivel my hand so that I can now curl my fingers in the direction of the push, the force itself. So fingers straight from the pivot point towards the location of the force, swivel until you can curl your fingers in the direction of the force. And now your thumb is telling you the direction of the torque. So the push in this case exerts a torque that's straight out of the board. which corresponds to the idea of a counterclockwise rotation, which is what this push should be doing. You exert this push, you're trying to make the board rotate counterclockwise. So we'd say the force of the torque from the push is outwards, which we usually draw as a circle with a dot. The circle with a dot is supposed to look like an arrowhead pointing straight towards you. What about the torque of gravity?
It's pointing into the page.
Yeah, torque of gravity, you got radius, force, so that's pointing straight in. And we generally draw that as a circle with an X in it. The idea is that, I mean, that's supposed to look like an arrow pointing straight away from you. The idea is if you've got an actual physical arrow, if you're standing over here looking at it, you just see the tip of the arrowhead. So this is supposed to look like an arrowhead pointing straight towards you. Or if you're standing behind it, you see the back of the arrowhead and you see the fletching, the feathers in the back of the arrow. So it's supposed to look like that. So an arrow pointing straight towards the viewer, an arrow pointing straight away from the viewer. And so those torques are in opposite directions, which makes sense because one of them is trying to make the object rotate this way. The other one is trying to make the object rotate this way. So we can just treat one of them as positive and the other one as negative, which is good because we want them to add up to 0. So we've got torque from gravity. I'm going to leave off the units here because it looks like everything's going to work out to Newton meters anyway. Torque from the push. We treat, let's say one of them is negative and one of them is positive. Doesn't really matter which is which as long as you're consistent about it. And they've got to add up to 0. So this is the sum of the torques adding up to 0. And now that we have this equation, how many unknowns are in this equation?
There's one.
Yeah, just one unknown, the force of the push. So now that we've gotten the torque equation with just one unknown, we can solve that equation for FP, add 100 to both sides, multiply both sides by the reciprocal, so that's times 5/6. We can partially reduce that. 100 over 6 reduces to 50 over 3. So 50 times 5 would be 250 over 3 newtons. So that's the force of the push. The person standing over here is pushing diagonally with a force of 250 over 3 newtons, which would be about 83 1/3. So we now know exactly how much the force of the push is. And if we wanted to, we can now take 4/5 of that to get the X component and negative 3/5 of that to get the Y component. But most importantly, what other equations does force of the push show up in? Where else do we have FP written in equations?
You have it in the equation where you have like fx and fy.
Yeah, if we take this back to these equations, we can substitute 250 thirds into these equations. And I would probably leave it as 250 thirds for now, just to make the calculations easier. Plug that into both of these, and then you can solve each one of those for the one remaining unknown. Because now that you know FP, this equation, the only unknown is force of the fulcrum in the X direction. This equation, the only unknown left is force of the fulcrum in the Y direction. So you can solve for each of those, and then you know the X component and Y component of the fulcrum force. And knowing that, you can use inverse tangent to find the direction of the fulcrum force as an angle, and you can use Pythagorean theorem to find the magnitude of the fulcrum force, how hard the fulcrum is pushing into the beam. So that's usually how you would solve a statics problem like this. Anytime you know that an object is not moving, no translational acceleration and no rotational acceleration, you can assume the forces add up to 0, which might even get you 2 equations if it's a 2-dimensional situation, X components and Y components separately. And also the torques have to add up to 0. That's a total of 3 equations. X components of forces add up to 0, Y components of forces add up to 0, and torques add up to 0. 3 equations means you should be able to solve for up to 3 unknowns. If there are more than 3 unknowns, you're going to need more information. to set up extra equations. But 3 unknowns, 3 equations makes a solvable system. Any questions on that?
So could you explain again how you knew that one of them was in the negative direction and one was in the positive in that equation, negative 100 plus 650? Yes.
Yeah. Well, we know they're in opposite directions in the sense that from the right-hand rule, the force of the push is an outwards torque. The force of gravity causes an inwards torque. So the torques are geometrically in opposite directions. And we generally represent directions. If we're just talking about along one dimension, like in this case, along this axis, we just choose one direction to call positive and one direction to call negative. For vertical direction, there's the usual tradition that up is positive and down is negative. For a sideways horizontal axis, there's the usual tradition that to the right is positive and to the left is negative, other way around. But for outwards and inwards, there isn't really a general consensus on that. You can basically just choose whichever direction you want to call positive and the other one negative. But the important thing is we know these 2 terms have to have opposite signs because they're in opposite directions. If I have the option, I usually choose the term with the variable I want to find to be the one to call positive, just because that saves a step later on. But it doesn't really matter which is which. In this case, you've only got 2 terms. You know they have to be opposites, so you just choose one to call positive and one to call negative.
But aren't both of them like in the same downward direction, like both the components that are in the negative y direction? So how would they be in different directions?
The forces are both pointing downwards, but these aren't forces, these are torques. And torque direction is not the same as the direction of the force. Like the push, we only care about the perpendicular component. So let's say the y component of the push is down, but the radius is to the left. So radius and force create an outwards torque. So force of the push is downwards, but the torque of the push is outwards. For gravity, you've got a radius to the right and a force downwards. So to the right and downwards creates an inwards torque. So the torque from the push is outwards, the torque from gravity is inwards. Even though the forces are in relatively the same direction, the torques are in exact opposite directions, because torque is not the same thing as force. And if you want to look at this more conceptually, you could say the force of the push is trying to make this rotate counterclockwise. The force of gravity is trying to make it rotate clockwise. So they're attempting to make it rotate in opposite directions. Even though it's the same direction of force, the forces are on opposite sides of the fulcrum, opposite sides of the pivot point. So they have opposite effects. Any other questions on that?
Oh, okay. Got it. Thank you.
You're welcome. All right, see you next time.